Right. Oh, so I don't forget. Who is your phone provider? Who are you all signed up with? Three. Now, how much are you paying?
20 euros.
You're paying
20 euros.
20. Everyone's paying 20. Are you in contracts or can you cancel?
Prepaid, yeah. Month by month.
Okay, because a new phone company launched today, and I just switched to them, and for their first 100,000 customers, they have this great deal, unlimited calls, texts and data for 10 euros.
Wow.
10 euros a month, yeah. So I just switched today, and I'll get my SIM card. I can keep my number. I can keep my number. I get my SIM card next week. So it's called GOMO, G-O-M-O. Yeah. So if you're wanting to save 10 euros a month, you can switch to them.
Are they cutting the price?
Huh?
How are they so much cheaper?
I don't know. They're just going really aggressive
Yeah.
for new customers. Yeah.
How is the signal?
Yeah,
I think the signal should be okay because they're saying that 3G is 97% coverage and 4G is 95% coverage. So
And do you get to use the unlimited stuff when you roaming?
no, roaming the 10 gigabytes.
Okay.
Yeah,
Like all of you.
yeah. So it's 80 gigabytes. It's unlimited, but it's never really unlimited. It's 80 gigs.
Yeah.
Well, no, actually,
Shaped.
it's 80 gigs. If you go over the 80 gigs, they just reduce the speed.
Yeah, so shaped,
Yeah. But anyways, if you want to check later today, have a look at their website.
Alright.
I can't tell you how good they are because I won't get my SIM card till next week. But I just thought because it's a limited offer for the first customers, you might want to know. Since you'll probably be in Ireland for the next 4 or 5 years or something like this.
Yeah.
Unless you're just going to the UK. You don't know yet? Not sure, no decision made yet. Alright, power and efficiency. You got that?
Yeah.
Okay. Right, so imagine you carried 1 kilogram up a hill, and now imagine 1,000 ants each carried 1 gram up a hill with you. Who's done more work? What do you think?
Done the same.
It's the same, yeah. Why is it the same? The mass carried is the same, and the distance carried is the same. But there's obviously something different in each situation. If you carry up 1 kilogram, or if you have to wait for 1,000 ants to march up carrying 1 gram each, there is something obviously different between the two situations. So, who did more work? The answer you. Let's calculate. It's the same, mgh. No difference in the mg or the h. So, we need a different concept now. Work isn't enough. We need to know how quickly the work is done. And this gives us the idea of power, where power is the rate of change of work per unit time. So as a formula, what would that be?
Work over delta T.
Yeah, work over time. And the units are joules per second.
So I wanted to ask,
Yeah.
why is the unit for mgh Newton meters?
For mgh?
Yeah.
No, it should be joules.
I mean joules. Yeah.
Oh, if you work it out as mg and h, how do you get joules? We can have a look at that after this definition.
Power also measured in watts.
That's it, so that's the next thing. This unit is also known as a watt. 1 watt of power is, well, you give me the definition. Use your own words. What would you say?
1 watt of power is 1 joule
Yes?
of work done.
Oh, more of a sentence, yeah. Your sentence is too short. Go, Zach, what did you say? 1 watt of power.
1 watt of power is 1 joule of
Yeah.
work
Yes.
done
Yes.
over 1 second.
There we go. 1 joule of work done in 1 second. So just before we go on really quickly, Zach just wanted to check, is the units for MGH joules? So the units will be kilograms, obviously, meters per second squared for G, and H, meters. Oh, okay. Now, remember that F equals MA. So the unit for F and the unit for MA are the same. So that's Newton and that's kilogram meters per second squared. So this fella here is the same as a Newton. And we know that a Newton meter is the same as a joule. So it does work out. Right. When you convert electrical energy into light energy, you've not used any energy. What's this rule called in physics? Conservation of energy. You've converted it. But the electrical energy was converted into light, which you want, and heat, which you don't want. In fact, how much power in a 100-watt bulb is in the form of light and heat? So, now not a fancy bulb, just a normal, old-fashioned, like the bulbs you see in the cartoons. Tungsten filament. Here's the bulb, and then there's the filament, and there you go. And let's say per second there's 100 watts, which remember means 100 joules per second. And two types of energy come out from this. You have your light, which is what you want, but then you also have heat, which you don't want. This is kind of like a waste, this heat. Okay. What do you think? Of the 100 watts, how much is waste and how much is what you want? How much is light and how much is heat? So what numbers do we think? Let's start with this side. How much of the 100 do you think is actually light? Okay, you're going 70, 30, so?
I'll go 40, 60.
Which way?
60 heat.
60, 40, okay. Any? You're going 20 for light and 80 waste, okay. Regina, what do you think? It's only a guess. What do you think? 30, 70. Which is the 30? The waste is 30 and 70 for light. Okay. Is that everybody? 1, 2, 3, 4. Who didn't give? Oh, Lee. What do you think?
I'll guess 50-50.
Good. 50-50. Even split. Good. Right. So the answer is waste is 99 and light is 1. Yeah. So you can understand why a lot of people want you to use the new light bulbs, the energy efficient light bulbs, okay? The energy efficient light bulbs, they tend to be not 100 watts, like I have them at home, they're kind of around about 4 watts. So it'd be 3 waste and 1 light. Now that's still, I mean, it's still wasting 75%, but at least you're only wasting 3 joules instead of 99 joules. So, it's a heck of a lot better. Okay? But this gives us our next idea, which is what we call efficiency. How well you use the energy. Efficiency. So, efficiency is a percentage. It's the percentage of useful output compared to input. So, here's the formula. Can you see? It's useful output over total input. Now, does anyone know this letter? It's a Greek letter.
I
Nope.
saw it yesterday when I was checking research for the thermal neutral thermal.
Which cinema? Huh?
Thermal neutral.
Oh, you saw this Greek letter?
Yeah.
Give us a clue, so
It's
which Pokemon does it sound like?
no, actually, it sounds like I think there's a terrorist group in Spain with the same name as this letter.
What?
In Spain, with this name of this letter, I think. Not 100% sure, but I think. No, you don't know your Spanish terrorists?
No.
ETA.
Oh, ETA.
You've heard of ETA?
Yeah, actually.
Yeah. They're Spanish terrorist group, aren't
I
they?
think so.
Yeah. I mean, they haven't done anything since the 90s. I think the last thing they did was bomb the train in Spain, wasn't it? So I don't even know if they exist still. Now, I don't know if it's just a coincidence, if their name just sounds the same as this, or they saw the Greek letter and thought, that'd be a cool name.
It's probably an acronym or something.
And it could be that too, yeah. Maybe Diego would know. When he comes back, we can ask him. Okay. So if you were to take the energy, now here's a good example, you know, maybe I should be calling it work rather than energy, but it doesn't matter. If you were to take the energy on the top and the bottom, if you took the energy on the top and the bottom and divided by time, what's energy over time or work over time?
Oh.
It's power. So another way you can write this formula is like this: total power out over total power in. It doesn't matter. My point is, you can use energy or you can use power. You can use joules or you can use watts. It doesn't matter. Yeah? Now, I have a little note here. Obviously, you would like it to be 100%, right? But it never can be 100%. It's always less than 100%. Tell me this. When you think about your home, what thing in your home might be closest to 100%? What do you think might be closest to 100% in your home? Well, we know it's not the light, that's for sure.
Microwave?
Do you know, I think a microwave would be pretty close to 100, yeah.
An oven?
An oven as well would be pretty close to 100, yeah. I think, well, no, do you know what? No. I wouldn't say an oven would be close to 100 because a lot of the heat actually is wasted because it comes out the front.
Yeah.
Because the doors actually, you can feel the heat coming out, so that'd be a waste. A microwave might be better, but I can feel some heat that comes out. Maybe that's wasted, I don't know. So what can we think now?
Water heater?
Yeah, electric heater. An electric heater would be nearly, so it could be a water heater, but I think, like, you know, those electric heaters in the room,
Yeah.
they'd be nearly 100, but they're not 100. What form is the wasted energy? Sound, yeah, because you can hear them, they go, little buzzing sound.
Oh,
Yeah, the coil ones, yeah. But they'd be the closest to 100% an electric heater, because the waste energy, that is the heat that comes off, is actually the thing you want, you know, so it's not really a waste then. Yeah? Okay, continue. Yeah?
Yeah.
So, a boy lifts a 2 kilogram physics book off the ground at a height of 1.1 meters. It takes him 2 seconds to do this. What's the power? Okay, so tell me, power is work over time. What form of work is he doing here? Yeah? Yeah, so he's doing work. What type of work is he doing? Lifting. So he is giving the book potential energy. That's what he's doing. When I lift this up, in terms of energy, you can think of it as me giving energy from me into this in the form of potential energy. So I'm doing work by giving this potential energy. So the formula work over time could be written as mgh over time. Yeah? Is that okay? Now just please make sure you're okay with that, because this confuses students a lot. What do we get mgh over t? 10.7 watts.
10.8 now.
Are you sure?
It's 10.7 now.
Okay, 10.8. Is that okay, Dorian? Yeah. He got his energy from breakfast. However, half the energy is wasted as heat. What is his power now? So it's a different answer. See if you can calculate. You need to use the formula for efficiency. Power out over power in times 100%. Okay, what's the efficiency? I said half is wasted, so I'm saying it's 50% efficient. Now,
Power in is 10.7.
no, that's power out,
Okay.
10.79,
So power
because that's what's coming out at the end, the lifting of the book. It's the power in that's different. If you solve this, you get x is roughly, I don't know, 22, what is it? 21 point, 21.6 roughly, isn't it? Isn't it? Yeah. Now think about this. It makes sense. If he has to do the same job, but he's wasting half his effort, then he needs to be twice as powerful. You know, like if you have a car engine and it's moving something, but maybe there's energy now being wasted, like perhaps somebody's pulling or there's friction or whatever, then the car energy needs to be more powerful to do the same job. The job is still the same here, lifting the book in 2 seconds. But because he's not efficient, he needs to be more powerful. Is that okay, Zach? You look a bit confused.
No, yeah.
Is okay? We can continue?
Yeah.
So, let's see.
Stephen used confusion.
Wasn't.
The time missed.
It's I'll get you next time. Right. A 1,200 kilogram car starts at rest and reaches a speed of 100 kilometers an hour over 10 seconds. If the car was 100% efficient, what is the power of the engine? Okay, now wait, I'll do this one with you. So, we have the car, starts at rest, and then it reaches, what did I say, 100 kilometers an hour?
Yeah.
Over 10 seconds, it's going 100 kilometers per hour.
Mass 1200.
And mass 1200, thank you.
It's more of a bus.
It is looking more like a bus now, isn't it, than a car. So first things first, we'll have to convert that 100. So what's that about now? 33, is it? Or
100 times
1,000 divided by 3,600. 27.78 meters per second. Now, what form of energy did this car get? Kinetic. It got in the end, it got kinetic.
Yeah.
Where did this energy come from? Who gave it this energy? The gas, or more generally the engine, the whole
Mechanical.
system, the mechanical system, yeah. So in other words, it got this from the whole engine, gasoline and everything included. So the work done was given this kinetic energy, which is going to be a half v squared. Right, now before you type that in, that's the work, but what I would really like is to divide this by the time to make it a power. Okay, so what's the power now?
46296.
46296. So
3.
that's, yeah,
Please confirm.
seems pretty big, but
No, it's around the same. There's got some slightly different.
but that's okay because we're going to do 3 significant figures. So that would be 46 kilowatts.
46.
First- Okay, fine.
0.3.
Oh yeah, sorry, 0.3 kilowatts.
That's about right.
Is it? What type of car would be a 46.3? Would that be low end or
That would be like a really small engine.
a micro
Yeah.
kind of size? Yeah. Okay. Yeah. Now, this is obviously not realistic because the engine's not 100% efficient. I pick a number, I think realistically you're talking about an efficiency of 40% for car engines. Maybe good ones like a hybrid or something like this could be maybe 50, maybe 60 at most, but I think 40 is a typical number for, yeah, you would think so too, 40%. So using this number now, tell me what the power is. And before you do, is the power going to be more or less now? More. Because remember, you still want the same output, 100 kilometers an hour in 10 seconds. But because it's wasting energy, it has to be more powerful to do the same job.
Shouldn't it just be divide 40%?
Basically, divide by 0.4 would be a quick way to do it, yeah.
115, no, 115 kilowatts.
What's a 115 kilowatt power car?
It's like a 2-liter engine.
Really?
Yeah. I'd say it's about an average car has that. Like a, it's an average car, Volkswagen Golf.
Something like this?
Yeah.
Can't remember where I was looking at all. I think I had a Toyota Yaris. Would that be like 55 or something kilowatts? I don't know. I remember looking this up before.
I think it's a little bit more.
Maybe 60?
Yeah, 60, 70.
Okay, yeah. Alright, we got that? Yeah. That one's a little bit too hard. So, a pump in a basement pumps oil from a tank at 6 kilograms per second into a boiler which is 10.19 meters above the pump. So, you've got some oil in here in a tank, and it's being pumped up. So like this could be, this could be underground in a house, in their basement or something, and in their house, perhaps, whatever, the boiler is upstairs or something like this if it's an apartment. Yeah, like if it's an apartment, yeah. The oil tank would be in the basement and the boiler might be up in the apartment suite. So it gets pumped up at a rate of 6 kilograms per second. And this height here, it travels, we said, is 10.19 meters. The oil enters the boiler at 2 meters per second. So the oil is being pushed into the boiler at 2 meters per second. It's pretty fast, actually. The pump is 75% efficient. So this little pump here, which is pushing the oil up, is 75% efficient. Okay. What is the power of the pump? Now, this is a little bit complicated. This would be an example of a hard exam question. There is one more that is a little bit hard. Both these I've seen on the exam, but they've only come up once or twice, so they're not common, but they're possible questions for the exam. And you'll see in the homework that there'll be one like this too. Let's have a look at this. So, what energy does the oil have at the moment if it's in the basement? Or, well, maybe not the basement, ground level, whatever. It has,
negative.
yeah, we'll put it at ground level. I know I said the basement, but just to make our life easy, it's ground level. So what energy does it have? Does it have kinetic?
No.
No, right now no kinetic, no potential, 0 joules. Okay? When the oil makes it up to the top, what energy does it have? Kinetic and potential, because it's both higher up and it's now moving. So if we are looking at it per second, at the top it will have a half m v squared, yeah, plus m g 10.19. What do we get, please, here? I think I did that on purpose to make this 612, 612, is it? Is it 612?
What is the plus to n? Because I think potential and kinetic is different directions.
No. Oh, I see. No, one up here it has kinetic and potential because it's moving in the boiler and it's also above the ground. So they're both there at the same time.
Oh.
Yeah.
611.8.
Yeah. Okay. So I was close. I was off by 0.2. So that's roughly 612 joules. Okay. Where did it get this energy from?
Pump.
From the pump. Did the pump do 612 joules of work, roughly? No. It did more, because it's only operating at 75% efficiency. So you can say 75% equals 611.8 over x times 100%. So that means x will equal 611.8 over 0.75.
815.7
So that's 816 watts.
watts.
That's the power of the pump. Okay. So like I said, this is a little bit harder now. Will we go on to the next example? Do you need to write this down? I think there are actually 2 questions like this in your homework, so maybe you should write this down if you don't have it. For efficiency? Eta, yeah, like this. Well, kind of like an N. Got that?
So when the movement is vertical, always need to like potential energy plus kinetic.
Any movement has kinetic.
Yeah.
Any movement, vertical, horizontal, doesn't matter.
But I mean, need to need potential when it's become vertical.
Potential is when there's a vertical movement, yeah. Shall we continue? Yes?
Yeah.
This is a hard one. I'll do this with you. It takes 30 seconds for a 1,495 kilogram car to reach its top speed of 214 kilometers an hour. What's the power of the engine? Right. Can you give me the speed, please, in meters per second? What's that? About, is it 50 meters a second?
59.
Okay. So let me draw this. There, we'll make it a bit more car-like. There now. Okay, what is this? 1495 kilograms And how fast is it going? What did you say, Dorian? 59.45? 44 meters per second. And it took it 30 seconds to get from rest up to this speed. Now, it's currently travelling at its top speed. So what do we know about the forces if it's travelling at its top speed? It's balanced, yeah. So there's a drag force here, and there's also a thrust force here, and they should be equal. Okay? Let's calculate the acceleration. U, 0, V, 30, A, don't know. Right? Sorry, no, I said, V, 59.44, A, don't know, T, 30, S, don't need to know. So can you give me the A here? I think just V equals U plus AT should do it, right? So what's the A? Okay. Now, Newton said F equals ma. M is 1495. A is 1.98.
2,962
newtons. Now, my next question is, what F is that on the diagram?
The resultant. No. It's the thrust force.
Is it?
But drag would also be that.
So then the total force would be 0. But you're right, this F is the resultant. But the resultant is 0.
So isn't it the thrust and the drag would be the same?
Yeah? Are they 2962 though? So I told you I'd get you next time.
No, the thrust is 2962 and the drag is negative 2962.
But that 2962 is the net force. But in this picture, what's the net force? 0 newtons. Now, I tell you, yeah? Do you know what's happening?
Instantaneous.
What's happening is you need to remember that the drag is a force that changes. So only at the end does the drag equal the thrust. But at the beginning, what was the drag? 0. So we need to replace it with an average. So if I draw it like this, at the beginning we have a thrust, and how much drag do we have? 0. And at the end we have a thrust, and how much drag do we have?
2,000.
D, we call it, yeah. But we said D equals T in the last picture, so that's actually a T here. Now, this is bad. We can't have two different drags. It's complicated. So let's replace it with an average. So if this is T, what would be the average drag? Well, what does it start with? 0. And what does it finish with? T. So what's the average? T over 2. Yeah?
T minus 0.
Yeah. T plus 0 over 2, the average. Now, what is the total force then in this picture forward? A half T. Yeah. T minus T over 2. So this number here represents half the thrust of the engine. So really, this T is 2962 times 2. So I told you this was a hard one.
Yeah.
It's a tricky one. So what is the thrust of the engine?
5924 newtons.
5924 newtons. Now, on to calculating what else? The power rating. But this actually isn't, this doesn't have efficiency in it. So, there's also a second problem now. Power equals work over time. Now, you could calculate the work here.
You don't have the distance.
Yeah, and so then you could calculate the distance, but there's a nice little trick. I want you to watch this trick carefully. It's useful for this. What's the formula for work? F times distance over time. Okay? But what is distance over time? Velocity. Fe. Okay? So you could use force and velocity, if you like.
So the total T times
The velocity.
59.
Yeah.
352 kilowatts.
Kilowatts. Now, this formula, note this formula here. This is not in the formula book. However, there was one question one year that required students to use this formula. I think most students forgot about this formula. Even though we did it in class, it wasn't in the formula book. They've never done an exam question with it, so it didn't occur to them that there's another formula for power. So you want to remember, maybe you might someday need this formula for power that uses force and speed instead of work and time. This is an alternative. Yeah, and this one's 100% efficient. Yeah. Can I borrow your calculator for a second? Just want to check something here. I think I was looking up some sports car or something. I don't remember what it was.
It seems a bit high, yeah.
Well, maybe let me just check something here.
Because 352 kilowatts is quite a lot for a 1,495 kilogram car.
Let me see.
And for it to reach 214 kilometers in 30 seconds is a bit long.
Let me see. Let's see. Oh, the time was 30, wasn't it? Is this right? Did you type this in right? Let's see.
What?
Is these numbers right? Something seems a bit suspicious. No, that looks okay. No, I think this is okay.
1495 times 1.98 is 2960.
Yeah, it's 2960. Why did I say 2962?
I don't think that changed it too much.
Yeah.
Oh, I just can't count on you, Zach. I just can't count on you. It doesn't matter. Just note that there may be some calculation errors in this.
Why did you say if I'm wrong, don't
We have to keep
That was
it.
the only one I didn't check.
And that he didn't miss an opportunity now to cause trouble.
Wait, 5, 9.
To keep an eye on Zach.
No, it doesn't change much.
Okay, fine.
Doesn't change at all.
Right. Continue. Yeah. Now, this answer isn't going to be perfect because the drag is changing. So you have to approximate the drag as being constant, right? Also, what I'm not happy about, to be honest, is I'm not entirely sure if the V here, should I have used this V? Or maybe I should have used the average V.
Yeah.
I don't know. I think I made this question too hard. Yeah, I did make this question too hard. I definitely made this question too hard. The only thing I would like you to learn from this question is this formula. So I think I'll make another example for the next group of students that is easier than this, that needs this formula.
If we use it, we would have to use average V?
I don't know. If you held a gun to my head, I might say yes, use average V. But to be honest, I'm not 100% confident. And the reason I'm saying I think maybe we actually have to use average V is because I used average force here in this calculation, because I had to use an average drag. Maybe. Who the heck knows?
Some physicists.
Some physicists would know. Not this one though. Or maybe not, because actually, now that I think about it, a lot of cars, their power rating is their maximum power.
Yeah.
So when you give the power rating of an engine, it's not the average power it had over its journey, but the power it achieved at the end as a maximum. So, no, maybe I take it back. Maybe I do use the V at the end. Yeah, I'll flip a coin. That's how I'll decide. Yes, I'm sticking with my original answer because most car engines give a maximum power output. We should use the final picture, its speed at the end, in calculating the power output.
Yeah, because the power wouldn't be horizontal anyway. It would be linear.
Yeah. And nobody cares about the average power when you want to know what the maximum power is. In fact, do I even say maximum in the question? Yeah, what's the power rating? It usually means the maximum. Yeah, okay. No, I take it all back. I do know what I'm doing. Okay, we'll give you a couple of minutes to try a few of these, and then we'll have a look at the next topic then, okay?
So could you just go back to the slide with ETA?
The formula?
Yeah.
This one?
I just want to check the bottom part heat loss. Yeah, I just want my words mixed up.
I can close this?
Just hang on.
Yeah, okay. Right, just give one or two questions a try and then we'll move on. I think the next thing is conservation, isn't it? Momentum. Yeah.